In this video, we're going to take a look at the properties of definite integrals. If you are in my class, I'm going to start with the warm-up, and if you're watching this from home, you should stop the video, you should do the warm-up in your packet, and then resume the video and check it to see how you did. If you're not in my class, you may want to move on to the lesson on the properties of the definite integral. In the warm-up, we have a function, and we have been instructed to evaluate a definite integral. Actually, I take that back. We've been asked to write that definite integral as a limit, which is something that we recently learned in our class. So if you take a look at the answer here, remember a definite integral is a summation. It's the accumulation of area bound by a curve, in this case cosine of x plus 2x, starting at x equal to -3 and stopping at x equal to 4. And we want to put in an infinite number of rectangles in order to accumulate all of the area. So the limit as n approaches infinity, whoops, edit, undo. So we're trying to put in an infinite number of rectangles, starting with the first rectangle and stopping with the nth rectangle. Again, in this case, that would be an infinite number. We're dealing with a right endpoint approximation. So to get to the first right endpoint, we have to start with the lower bound, which is -3. So -3 plus, and we're going to have to move a common width to get to the first right endpoint. The common width is b minus a over n. So -3 minus 4 over n, which gives us 7 over n. Oh, I did a minus b, sorry. B minus a over n. I knew something was wrong. So that gives me 7 over n for a common width, and the I is how many times we're going to do it. It's our counter, the first right endpoint, the second right endpoint, the third right endpoint, etc., etc. And we're going to substitute that in place of every x of the function. So cosine of x plus 2x, and then we're going to multiply by the common width, because this part right here is the sum of the heights that are generated by a right endpoint approximation. Number 2, in terms of particle movement, what does the definite integral in number 1 represent? Well, in terms of particle movement, it represents the change in position of the particle from -3 to 4, or you could say it represents the displacement of the particle from -3 to -4. There aren't any units given in this particular case. And we can safely say that because we haven't looked at the graph of the function yet, and we don't know whether the area is positive or if some of the area is negative, so we have to say the change in position. Number 3, examine the graph of the integrand using your calculator. Does the particle travel more left or more right? Justify your answer. Well, down here below I have the graph, and so we're going from -3, which is, oops, edit, undo. We're moving from -3, which is about here, to 4. So basically we're comparing this area, because in this region particle would be traveling to the left. Again, this is assuming we have a velocity function. This region particle traveling to the right, and from my visual inspection it looks like to me that the area from in this region, the positive region, is greater than the area in the negative region. So let's see what I actually said. The particle travels more to the right because there is more area above the x-axis than below the x-axis over the interval. And then finally, number 4, we're going to use our calculator to determine the displacement. And so I have pulled out my calculator. And if you have a newer model, remember it will operate a little bit differently than mine. It's actually more intuitive on the newer models. So I'm going to put in my function, which is cosine x plus 2x. Let's see what mode I'm in. Yep, we're in radian, so I'm going to do a zoom 7 window, just to take a look at the graph again. I need to open up a little more in the Y. I'm going to go to the home screen. I like to do the integration there. If we're going to determine the displacement, remember we want the negative area to stay negative and the positive area to stay positive. So I'm going to do math number 9, which is fint, and I'm going to call up my function that is in y number 1. I could type in the function again if I wanted to, but I've already put it in my calculator. I am in terms of x. I'm going to start at a lower bound of -3, comma, and then an upper bound of 4, close the parenthesis, and this will give me the displacement, which is 6.384. If you have a newer model calculator, again, you actually get an integral on your calculator, and it's a little more intuitive. The second thing that they asked us to calculate here, I believe, was the total distance traveled. So to do that, I'm going to pull up what I had before. I'm going to go second, enter, and that pulls up the what I typed in last. And all I need to do is to put an absolute value. So second insert, math, an absolute value around my function, because now I'm trying to force all of the area to be positive. So I inserted an absolute value, enter, that forces all the area to be positive, which will give me a total distance traveled of 24.567. If you're having any trouble with your calculator, please come in and see me. I'll be glad to help you on that. And let's see if my answers agree with what I just got. So we have 6.384, which is what I had, and 24.567. All right, let's go to the lesson now. Properties of the definite integral. I have a curve given at the top that I may use to reference or explain some of these properties. Some of these properties are very straightforward, and you actually already know them, but they haven't been made formal. So the first property says, so let's say that x equal to a, get a pencil, let's say x equal to a is right here. If I collect the area starting at a and stopping at a, there's no movement whatsoever. So basically, the area that I'm collecting is an area of 0 because I haven't moved anywhere. So if I start at A and I stop at A, the amount of area that is accumulated is a net of 0. Why? There is no change in x. Number 2, the area starting at A, and we'll make this B right here. So this is A f of A and B f of B. The area from A to B is equal to the opposite of the area from B to A. In other words, when you change direction, you change the sign of the area. We're accumulating in the opposite direction. Number 3, let me get rid of this, Number 3, if we collect the area from A to B, and then we pick up again, and we collect the area, from B to C, and B is between A and B. So we have, we'll see, an A, a B, and a C. So if I accumulate the area from A to B, and then I accumulate the area from B to C, which is right here, then obviously I have accumulated the area from A to C. Not really going to say I mean, it's just kind of common sense. We're following order. And all it really says is we can divide the areas up into smaller regions if we need to, or if we don't want to divide the area up in smaller regions, we can go straight across. Number 4, k is a constant. K is a constant. So if I have a constant, I can, instead of having the constant multiplied by the function, I can pull it out front and make this k times the integral from a to b of f of x dx. K is a constant and can be pulled off the function. Number 5 says if you're going to accumulate the area of two functions, f of x plus g of x, you can, instead of accumulating the area over the entire function, you can break that into smaller parts. You can accumulate the area from a to b of f of x all by itself, and then accumulate the area from a to b under g of x all by itself, and then add them together. It's the same thing. You can take that sum and you can break it apart and accumulate the areas individually. Number 6, if f of x is an even function on the interval a to b and f of a is equal to f of b. So in other words, if I just draw a simple parabola, let's pretend that's symmetric. Here's a, here's b. F of a is equal to f of b. In other words, they have the same y value. Then the area from a to 0, I should have started with this one being a. Let me fix that. This is a, this is b. Okay? So the area from a to 0, which would be here and here, hopefully it's obvious to you that that would equal to the area from 0 to b. In other words, they have equal areas. So the area from 0 to a of f of x is equal to the area from 0 to b of f of x dx because it's an even function. Number 7 says now I have an odd function. So our most famous odd function is y equal to x cubed, kind of something sort of like that. And we're going to call this a, and we're going to call this b, and these are partner points. So f of a and f of b. Notice that these areas are not equal to each other, but they're opposites of each other. So the area from a to 0 is equal to the opposite of the area from 0 to b of f of x dx. And all you have to do to verify that is to sketch a graph of an even function or an odd function. All right, let's apply those properties. If you look in your packet, so we've been given some information about a function f of x, but we don't have the graph of f of x. We know that the area from 0 to 2 is 2, the area from 1 to 2 is negative 1, and the area from 2 to 4 is 7. So what I'm going to do, let me move this page number out of my way, make a little space up here, is I'm going to create a little number line, and on that number line, I'm going to go from 0, I have a 1, a 2, and a 4, and I'm not trying to make them be symmetrically or equally spaced apart. I just want a place to record these areas. The net area from 0 to 2 is 2. So I'm going to put that on my number line. The net area from 1 to 2 of f of x is negative 1. And I put my negatives below just to remind me that they're negative. So that's from 1 to 2. And then the area from 2 to 4 is 7. So now that tells me if the area from 0 to 2 is 2 and the area from 1 to 2 is negative 1, then the area from 0 to 1 has to be 3. Why? Well, 3 minus 1 gives you an area of positive 2. If the area from 0 to 2 is 2, and the area from 1 to 2 is negative 1, then 3 minus 1 makes 2. So I know the area of that particular region. So I have the net areas of all of my regions on my number line. So I'm going to use that to answer the following questions. Letter A, evaluate the area from 1, so we're dealing with A, from 1 to 4. Well, we already know that the area from 1 to 4 is going to be negative 1 plus 7, because the area from 1 to 2, because this is the same thing as area from 1 to 2. I'm using my properties on the other page. I'm breaking this apart. Plus the area from 2 to 4 of f of x dx, which was negative 1 plus 7, which gives me a net area of 6. I would encourage you to stop the video at this point and try all of these by yourself, and then resume the video to see if you agree with what I got. All right, let's go on to letter B. I want to change colors of the pen here. In letter B, we're going from 0 to 4 of 3 times f of x. So we can rewrite this. Remember the property that we had about coefficients. We can pull that out front. And to go from 0 to 4, that's the same thing as 3 times the area from 0 to 2 of f of x dx plus 2 to 4 of f of x dx, which is 3 times 0 to 2, the area is 2. 2 to 4, the area is 7. 2 plus 7 is 9 times 3 gives me a net area of 0 to 3 times 0 to 4 of 27. Okay, moving on to letter C. I'm going to erase A to get so that there's not so much writing and so much stuff up here. Okay, letter C asks us to evaluate the area from 0 to 1, and we already did that. So the area from 0 to 1 is 3, and we talked about why that's 3. Let's go on to letter D. Let me erase all of this. Letter D, f of x plus 1. Now remember from your algebra experience that x plus 1 shifts the graph left 1 unit. Now we can play with going back up to the number line and shifting the graph 1 unit, trying to figure out what that does, but I think it's a little bit easier. This tells us to add 1 to all of the x values. So this is the same thing as the integral from, if I add 0 plus 1, I get 1. If I add 1 plus 1, I get 2. In other words, the area from 0 to 1, if I shift the original graph to the left 1 unit, is the same thing as collecting area from 1 to 2 of the original function. You might want to play around that and listen to that again and look at it and see if it makes sense to you. But what I did was, basically, the graph was shifted to the left 1 unit. I unshifted it. I moved it back to its original position by adding 1 to the given x values. So then I can look at my number line and see the area from 1 to 2. The net area is negative 1. Letter E, we are collecting area. Now this time it's f of x plus 1. This is a vertical shift, not a horizontal shift. So I'm going to break this problem up to say it's the area from 0 to 1 of f of x. Remember the properties on the other side. If I have two functions added together or subtracted, I can break that up into individual functions. So the area from 0 to 1 of f of x, we already know, is 3. The area from 0 to 1, so let me pull this out over here. The area from 0 to 1 of 1 dx. Think about that for just a second. Basically, we're starting from 0 to 1, and we have a rectangle that is 1 unit tall. So we have a 1 by 1. So all we're really doing is calculating the area of that rectangle, which is 1 by 1, for a total area of 1. So 3 plus 1 is 4. Now, soon you're going to see how to actually evaluate that definite integral analytically, but right now we're going to deal with it geometrically. Now, again, graphically, we have the line y equal to 1. That's where that 1 is coming from. So the width of our rectangle is 1 unit. The height of our rectangle is 1 unit, which is really a square. It doesn't look like it the way that I've drawn it. Okay, let's go on to letter F. In letter F, we have another horizontal shift. It's to the right 2 units, but remember what I said in letter D. To shift the graph back, I'm going to subtract 2 from these x values. So 2 minus 2 is 0, and 4 minus 2 is 2. That takes me back to the original graph, and the area from 0 to 2 is 2. That's the easy way to deal with that. All right, and then let's look at letter G. Let me clear some of this out of my way. Okay, that's all gone. So letter G, we have another vertical shift, which is like letter E. So this is going to be the area from 2 to 4, 2 to 4 of f of x dx minus 2 to 4 of 2 dx. We know that the area from 2 to 4 is 7. Now calculating this area, again we have the function y equal to 2. So there's the line y equal to 2. We're going to start at 2, stop at 4. So this is going to be 2 units by 2 units for an area of 4. So 7 minus 4 gives me a net area of 3. Let's see. I'm not concerned right now about H, I, and J, although I kind of want to look at them. Let's jump to the next problem at the bottom. The graph of y equal to f of x is shown below. Estimate the values for, let me get rid of that. Estimate the values for the net area from 0 to 3 of f of x. All right, so from 0 to 3, so to estimate this area, that would be kind of a pain in the butt because it's not very geometrical in shape. I'm really going to focus more on the area from negative 3 to 3. The big idea being we have an even function here. So the area from negative 3 to 0 is equal to the area from 0 to 3. Other than that, I'm not really going to try to estimate those areas. If it were a little more geometrical, maybe I would estimate those values. But that gives you a good idea of using some of the properties of integrals. There's a little more here that we could do, but I think we're going to stop it there. So that's all for this one.